All right, how's it going, everybody? We are here. I am making this video on Sunday, March 7th, right now. And today we're going to talk about section 7.3, the Runge-Kutta method. This is going to be our final topic associated with our numerical unit here. We're going to get our most powerful estimation technique here today. And therefore, one of the really important things to do today to conclude with is to kind of prove that this is our most powerful prediction method, not just to sort of claim it here by doing a little bit of error analysis like we did in our last video. So just to sort of recap what we've done here, we first learned Euler's method, which was it's just a straight up y equals mx plus b update. You start with b, you update by mx to get to your new y value, and you repeat that process. We applied Euler's method to both single ordinary differential equations as well as to systems. Then we improved Euler's method by considering the slope at two adjacent steps in the process, right? So instead of just considering one time, we considered the current time as well as the predicted location at the future time. Today we're going to upgrade to include a third point in time. There's actually going to be 4 points on the graph, three different unique time values that are going to be used to help us make an even better approximation of the appropriate direction in which to move in the phase plane to update our y value. So we'll use the variable x today. Today our goal then is to look at the Runge-Kutta method. The formulation of the Runge-Kutta method is a little bit complicated to understand, but it's really not that hard to use. We just have to do a little bit of bookkeeping like we did in our last video. We tracked the two different slopes, m and n. We're going to get four different terms that we're going to keep track of today instead of just two. So there will be a little bit of bookkeeping along with it, but that really just lends itself really well to programming then, and just even worse to by hand calculations here. And again, my focus on today wants to be on a little bit more on the error analysis, on saying how much better does Runge-Kutta do as we increase our number of subdivisions compared to Euler's and improved Euler's, right? So this is going to be one of those ones where I'm kind of just going to give you the formulas that we want to use. The important conceptual part at the end is understanding how this technique, what its relationship is with the errors as we increase our number of subdivisions. So let's remember our analogy from the last video. In the last video, what we kind of said, our analogy with Riemann sums was that Euler's method, our simplest case right here, it was a lot like our left and right hand rule for Riemann sums. It's the simplest possible thing that we could ever do. We're only using one x value. I said here one time value, but I mean one like x positions y value to compute a height in a Riemann sum. We're using only one times slope in the Euler's method. Then improved Euler's method is a lot like the trapezoid rule for Riemann sums. We're using a current time as well as a later time, finding the slopes at each of them and averaging them. Just like with the trapezoid rule, you find a height at one x value, a height at a different x value, and find the average of the two heights. So that would use two different input values for Euler's method, or for the trapezoid rule, and for improved Euler's method. Today, for the Runge-Kutta method, it's going to be a lot like Simpson's rule for Riemann sums. Simpson's rule is the rule that uses a parabola to estimate the area underneath one Riemann rectangle instead of a trapezoid or a rectangle. I shouldn't say Riemann rectangle. The area underneath one chunk of a parabola for the Simpson's rule there. And the Runge-Kutta method is going to do something similar to that. We know that for parabolas require 3 points to identify where a parabola is located exactly. And so we're going to use three different time values, or three different x locations is what we need. One of the small differences that we're going to see, though, is that the Runge-Kutta method is going to use two different heights associated with the middle of the three time values that we're going to use. So there's actually going to be 4 points that are involved spread across three unique time values out there. All right. So very, very similar to the improved Euler's method. What we're going to come up is, in a sense, of four different slope estimates, and we're going to consider a weighted average of those four slopes to be the slope we actually use to update our actual solution's position at that given time, at the next time step there. And also, just like with Simpson's method, we're going to weight the middle terms slightly more heavily than we weight the end terms. If you remember your Simpson's rule formula, it's got has coefficients of 1, 4, 2, 4, 2, 4, 2, and it ends with 1. So the outside two coefficients got the least weight, and the ones in the middle got more weight. We're going to see coefficients of 1, 2, 2, 1 on our weighted average. So the middle ones are going to get weighted a little bit more heavily. The exterior ones will get weighted a little bit less out there. So here's what we want to do. And again, today is not just about the Runge-Kutta method. It's about comparing the Runge-Kutta method to the other techniques by looking at the errors that are associated with them. So we're going to look at one big example today. And I just kind of want to tell you guys, I guess before I scroll down any at all, today is going to be quite a bit different than the previous days. Just in that you guys have essentially already seen all of the code. I'm going to write this code in a little bit different of a way, but nothing I'm doing is different. I'm going to like name some variables a little bit differently here. The other thing is that in the last video, like I typed out 100% of it in the video. In this video, I've already got 100% of it typed out, and I'm just going to talk through it because I don't think it's as I don't know. I don't think it's as a directly useful use of your time to watch me type out the code since you've kind of already gone through 4 of these videos with me. Or I guess this is the 4th video of you guys doing Python code with me. So today I'm just going to sort of have it already and be like, look at this. You already recognize this, and kind of move on to the next step since I think you guys kind of you get the flow of what we're looking at. I'm also going to use a little bit different variable naming conventions here. Part of the reason I feel like it's valuable for me to do this is just so that you guys can kind of see that a lot of the things that I've been doing in my code, I almost just said the word preemptively right there, were choices that I made, not necessarily a way that this has to be done, but one of the many ways that we could write the code that does this. So the code for today is going to look a little bit different, but I'm positive that you're going to be able to recognize that the math is the exact same. So I'm going to try and talk through what my code does. And again, I expect that you guys are going to recognize a vast majority of this right here. You've already kind of seen most of the code that's going to appear today. The only thing that's going to be brand new to you in this video is how do we compute the Runge-Kutta method update? That's the only thing that's new. That's like 5 lines of code out of like the 80 lines that you're going to see right here. All right? So let's go ahead and do this. And keeping in mind, our one question is, why do we abbreviate the Runge-Kutta method as RK4 instead of like RK or RKM? What's the 4 mean to us right there? We want to answer that. That's sort of our conclusion today is, what's that 4 mean in the shorthand right there? So what we're going to do is we're going to look at a simple example. We want to use examples that we can actually get the exact answer for, because otherwise we can't do error analysis, right? We don't know how far our estimates off are from the true solution if we can't get a true solution. So we're going to pick a differential equation for which we could actually just solve it and get the exact answer so that we can see how our estimating techniques, how well they do in approximating that answer. So the example for today, let's use all 3 of our methods to estimate the value of x of 4, so that the solution at time 4 using 20 subdivisions for all 3 methods for the initial value problem for this differential equation. So dx dt equals x plus t, very simple. You should recognize that this is linear, so you for sure can find the solution for this, which I already did down here. We're going to use the initial condition of 0, 0. At time 0, x is going to be at position 0. And we're going to go ahead and we're going to repeat this process with 40 subdivisions here. So we're going to consider how the error for each technique changes, given that we've doubled the number of subdivisions here. So we should notice that this is linear in x, so we can solve this equation pretty easily to arrive at the solution x of t equals, gosh, I wish that would highlight a little bit. Oh yeah, I can just click it right there. So here's our particular solution associated with this differential equation. If you use your integrating factor right here, we can come up with this guy. And we'll use this to compute the actual solution to compare our estimates against, right? We need to know the true solution or else we can't do any error analysis here. So let's go ahead and do it. We know what the structure of this code is going to look like. We're going to import the necessary libraries. We're going to define some initial parameters. We're going to perform each of our 3 estimating techniques, and then we're going to produce a graph to look at them. After doing the graphical stuff right here, we're going to go back and we're going to repeat the whole process using 40 subdivisions instead of 20 subdivisions. And then we want to ask ourselves, given that we doubled the number of subdivisions, what happened to the error in our final estimates for each of our 3 techniques? That's going to be our conclusion to kind of wrap all this up right here. So let's do it. So as you guys have seen, we're always going to start with our import to the top. It's just good Python coding. It's a style thing, but that is like a universal standard for style right there. Nobody doesn't do this, right? So always import to the top. We're using NumPy and Matplotlib, again, our 2 standard libraries that we need to use right here. So I'll go ahead and run that cell. We know that we need to define the functions that we're going to use here. We've got our differential equation function is dx dt equals x plus t. We've also got our solution equation right there, negative t minus 1 plus, this is, remember, NumPy is going to do exponentiation base e for us. So this is just e to the power of t is all that guy is right there. And that's, yeah, I had the right equation right there. So we've got the 2 functions that we're going to need here. For this example, and this is kind of me just kind of being more explicit about my directions here, I'd like to produce a graph. And what I want on this graph is I want to have the graphical estimate using all three different solutions. So that's three different curves. Plus, I want the actual solution curve plotted on there. So we're really going to produce a graph that has four different graphs on it. Euler's methods approximation, improved Euler's approximation, Runge-Kutte's approximation, and the true solution. I want all four of those together so I can kind of see how they relate to each other. We're going to produce this graph only with our 20 subdivision setup, partly because the higher number of subdivisions we go, these are all going to hone in on the correct solution, and I want us to be able to like see a visual distinction. So we're going to do a really small number of subdivisions here so that they're kind of like visually separated from each other. After we do that, we're going to repeat, but without making a graph, all that same exact code with 40 subdivisions. So we're just going to do a ton of copy and paste there. And what we want to do is say, what did the errors look like for all three techniques with 20 subdivisions versus what did the errors look like for all three techniques with 40 subdivisions? Since we're doubling the number of subdivisions, we want to come up with a general statement as to what happened to the errors with our estimates, given that we doubled our number of subdivisions. Finally, in the last video, we did a little bit of this comparing between two techniques, and I'm going to follow my same like numbering scheme that I came up with for this. Everything that has the number 1 attached to it is going to be tied to our Euler's method. Everything with a number 2 is going to be tied to improved Euler's method. Everything with the number 3 is going to be tied to the Runge-Kutta method. So we'll do our estimates for 20 subdivisions and 40 subdivisions with techniques 1, 2, and 3. That's our 6 total estimates that we want to come up with, 6 total errors that we want to compare at the end right there. Right? So that's our broad plan here. So our goal is to estimate the value of x at time 4 with 20 subdivisions for all three techniques, graph all three techniques, also graph the true solution. All right, that's our first goal right here. So let's go ahead and initialize the values that we're going to use. And as I told you guys, I'm going to use some slightly different variable names here today. I think that I've been using, honestly, some weird variable names. I kind of feel like a little bit better with the ones that I'm using here today. And again, the point is it doesn't matter. You should be comfortable in a programming setting defining variables that make sense and are practical for you to use. Decide if you like the ones that I'm using today better or worse than the ones that we used before. Follow that kind of style for yourself in the future. So what we know is that we need to know an initial time and a final time. So I'm calling that today TI and TF for time initial and time final. Especially for those of you that are physicists in the room here, T sub I and T sub F are very common things used for initial time and final time in lots of physics applications there. Today, I'm going to use, instead of the letter N, I'm going to use the word steps right there. I've been using N for N subdivisions, but what we know is that we typically use the letters M and N as our two slope estimates in improved Euler's. And so I'm going to leave that letter N alone for the improved Euler's naming scheme out there and call this what it is. It's our number of steps. It's our number of subdivisions right there. And we're starting with 20 subdivisions. Later, we'll change this 20 to a 40. We know that we compute our delta t, dt, as the final time minus the initial time divided by the number of steps right there. So again, a little bit different variable names, but you recognize all three of these parts. So step 1, let's go ahead and do Euler's method. Now, again, I'm noting here that I'm going to use a slightly different naming convention today to hold our lists. Rather than lists like Y list and T list, that's just going to get a little chunky today. I'm going to use something that's even more abbreviated here. What I'm going to do is I'm going to use capital letters to indicate lists, lowercase letters to indicate the values that go within those lists. So I would, for example, put a bunch of lowercase x values in the capital X list. More specifically, we're going to use things like the x1 list is going to, x1, I know it's a list because it's a capital X, and it's going to be tied to our Euler's method stuff because it's got a 1 on it. Capital T, I know, is a list. It's a list because it's a capital letter, and it's going to be tied to the Euler's method stuff, which is why it has the 1 on it right there. So again, using a little bit of a different convention here, but you guys recognize all this stuff. I want to say, in this case, my current time and my current x value are my initial time, and we're starting with x being 0 right there, right? Now, I'm going to initialize two truly empty lists. We've been doing this np.zeros to build a list with zeros and plopping things, overwriting those zeros with their correct value. Here I'm going to truly do empty lists. So rather than overwriting the value at the ith location, we're going to append a new value to the list, stick something onto the end of the list that wasn't there before. And you can see me doing a little bit of this right now. So I'm making the T1 and X1 just empty lists right there. And the very first thing I'm doing is saying, well, the first thing in the T1 list should be the current time. time initial, the very first thing in the x1 list should be the current x value. Notice that's a lowercase x, and that's my current x value of 0 right there. So right now, each of these, at this line, each of the lists are empty. After each of those two lines run, each of the lists have one object each in them. We have appended one object into each of the lists. And notice that my choice of variables here, the reason I'm setting it up this way is because these statements down here I think are way, way clearer now. So I want to do a grand total of steps, number of steps right here. So for I in range steps, where steps currently has the value of 20, so it says repeat all this action 20 times is what that's saying right here. What do I want to do? Well, I want my new value of x to be equal to the old value of x plus our slope at the current time and position, and I want to do that for delta t units of time. So x has been changed. I am then going to place the new value of x into the x1 list. I also need to update what my t value is, so I'm going to increment t by delta t. That plus equal says make t bigger by this value delta t right here, and then I'm going to go ahead and stick the current value of t into the t1 list. Every time it cycles through this for loop, it's going to update what x is, update what t is, put that x in the x1 list, put that t in the t1 list, and then go back around for another lap. Update, put them in the list. Update, put them in the list. Do that 20 total times, right? So we can go ahead and run this guy right here. And just because we're, responsible coders right here, we should stop for a moment and say, did this work out like I thought? Like, what's my T1 list look like here? And from my output here, I can see we are counting by 0.2 at a time. We are getting out to 4 right here. And you guys should notice something that probably hopefully makes you a little bit uncomfortable, as it should make any mathematician a little uncomfortable. Why the heck am I not just getting 0.0, 0.2, 0.4, 0.6, 0.8, 0.0 right here for all these guys? Well, this is an artifact of the fact that programming languages are always operating in base 2, and it turns out some numbers are much harder to represent in base 2 than other numbers. And so here it's getting as close as it can with powers of 2, but sometimes it's hard for it to get an exact number. It turns out that 0.6 as 3/5 is 3/5, it turns out, takes a lot of fractions being added together that are all 1 over 2 to the power of something to get there. And you can see that it struggles to get there exactly, and that's why we get these little artifacts of that one. That'll always happen right there. If I just do 3 divided by 5 right here. Oh, it does. I think that honestly, it's not really getting 0.6. I think that Python has some built-in things to say, ooh, I know that I should be truncating that for that person right there. So I don't know. You see these things out here when you do. I feel like anyway, whatever. We saw the T1 list did what we thought, give or take a couple decimals at like the 16th place out there. I can also see what my X1 list looks like right here, and it looks like we are, we're ending at a final approximation around about 33.33 right there. So I've got some X values in my list. Now let's do our improved Euler's method. We also saw this in the last video. Again, I'm going to reset my current t and my current x to be the initial time and the initial value that we gave for x. I'm going to make two blank lists, or not blank lists. When I say blank list, I kind of think of my list of zeros that we overwrite. Here, these are empty lists to which we add to them, append to them. So two empty lists. I'm going to append in those current values into those lists. So after these 4 lines run, we do have 2 lists. We do have a current t and a current x, and the 2 lists each have the 1 entry in them that they started with. We're going to go ahead and we're going to do our 20 steps right here. What we learned in the previous video is that we want to get 2 slopes, what we called m and n, and we're going to average those 2 slopes to tell us in what direction we should move to update x. We know that the m slope came from just computing our differential equation at the current time t, the current position x. We know that the n slope came from looking at our slope from our differential equation at the next time, which is t plus delta t. It's at delta t units of time later than our current time, and at our updated x location. But what we really wanted was like the next x time, or x value, but we don't know it. So what we do here is this is the estimate for the next x, according to Euler's method. This is Euler's method getting us our next step in times x plus our slope at the current time and current x value times dt. This gets us our future x right there. So we've got our current slope, our future slope, and we're going to average our current and future slope to get the true slope that we're going to move in to update our x value using improved Euler's. So now this says, let our new x value be equal to our old x value plus how much we need to adjust by, which is the average of the 2 slopes and we're going to do that for delta t units of time. We also want to update our current time. So we updated our current x, we're going to update our current time, and then we're going to stick both of those into their respective lists. The x2 list gets our new x, the t2 list gets our new t. I'm going to go ahead and run this cell here. And once again, we should just double check that this is doing what we thought it was going to. You should notice that our T2 list is identical to our T1 list. In fact, I think I can even ask it, Python that. Is T1 equal to T2? True. Yes, it is. These are exactly equal to each other. Technically here, we don't need to be tracking T2 because we knew it was going to be the same as T1, but I don't know. I'm saving more than I need to be saving right here, but maybe it's just good bookkeeping in case we want to change things partway through. We can see an X2 list here, though. These are the X values. Remember that our previous one got our final estimate out to like 33.33. This one's getting a final estimate of like 48. So we can see that Euler's versus improved Euler's, pretty massive difference in our final estimate right here. But only doing 20 subdivisions, I'm not terribly surprised. I expect there to be some error here with this few subdivisions. So now let's go ahead and hit up our Runge-Kutta method. What I'm going to say is let's go take a look at a diagram right here. As I told you guys, I'm not going to really sit here and break down the math behind why the Runge-Kutta method looks like it does. But let's go ahead and see a diagram that kind of shows us what's happening here. So here's our Runge-Kutta method diagram. And as promised, here's the things I want you guys to look at in the diagram. First thing is this. Look down here at your t-axis. What you can see is that there are 3 relevant times that are going to be used. Notice that this diagram is using h in place of delta t, right? T to our next t. H is our delta t. It's our next step in time. You should notice that one of the interesting things that's happening right here is that we're using half delta t steps right here. That's delta t over 2 that we're looking at. Sorry, I have been using my mouse on the wrong screen right here. I'm sure you guys have been watching along right here. Time axis, 1 delta t actually covers us over 2 different time steps that we want to be using. So here's half of a time step. Here's a whole time step later in time. Now, the difference, though, is that we're not just using 3 points because there's 3 time values. There's actually 4 points, and you can see them in red right here. So here's our first one. Nothing weird going on right here. But here we're going to look at 2 different slopes that we might be using, 2 different adjustments that we would make, both from this middle time value at time plus half a delta time, and then a slope, a vector relative to our full step in time later. This one is a lot like our improved Eulers. Improved Eulers is a lot like we're just using the first and the fourth here. Runge-Kutta is going to include 2 additionals. So what you can see here is that these vectors are named K1, K2, K3, and K4. So what we're going to do when we write our code here is we're going to compute those 4 variables right there. And we're going to take the weighted average of these 4 vectors right here to come up with the one vector that's going to instruct our motion how to move forward. Remember that I said at the beginning here, we're going to weight each of these. This isn't going to be a true average between these 4 objects right here. If it was, we would add up K1, K2, K3, K4 and just divide by 4. We're instead going to add up K1 plus 2K2 plus 2K3 plus K4. Since we added up 6 total components, 1, 2, 2, 1, we'll add those 6 parts up and divide by 6. That's a weighted average right there that we're going to take across these 4 vectors that we're building here. You should also notice that the heights at which we're making these estimates are dependent on previous values. So notice here, our y0 and our t0 is all we need to get k1. So k1 is just f of ty or f of tx. To get k2, K2 is going to be dependent on our current time plus half of a time step, and it's going to be based on a location that is our current location plus, notice it depends on us knowing what K1 was. So K1 is going to help us get K2. K2, notice, is going to help us get K3. K3 is going to help us get K4. So we have to generate these one by one right here. You can't just individually compute K1, 2, 3, and 4. You have to compute K1, K1 to get K2, K2 to get K3, K3 to get K4. So they all depend on their previous computation to get the next. So this diagram right here is all I used to write the code that you're about to see right here. The only thing that's different in my code versus this diagram is I'm using dt, where this diagram uses h and nothing else. The other thing is that we can't see in this diagram the weighted average components, again, where the weights that we're applying to each of these parts are 1, 2, 2, 1 for each of the 4 parts that we're adding up. Let's go ahead and see it in our code right here. So as we've been doing, we're going to initialize our current time and our current x. And again, the reason that this code goes in every one of these blocks is because t and x keep getting updated, right? T and x are something new every pass through this for loop. I want to use those same variables, but I need to kind of start over again, right? So this is me reinitializing these back to their initial values because they've gotten used before. I'm wiping away that old information by overwriting them back to their initial values here. I'm going to build my empty lists. I'm going to put my initial values in those empty lists. And here I go again. I'm going to say, go ahead and do 20 steps. And what we need to do is we're going to compute K1, 2, 3, and 4. We're going to use K1, 2, 3, and 4 to update our value of x. We're going to update our t, and we're going to stick x and t in their respective lists. We're using lists with the number 3 to indicate it goes with Runge-Kutta. And you can see, as promised, these are doing exactly what the diagram instructed. K1 depends only on our current time and on our current position. Right? K2 is going to depend on our slope, f, evaluated at time plus half a time step later, as well as our position plus K1 over 2, half of our K1 value. And notice one really important thing here I want to point out to you guys that's a little bit different. I'm going to scroll up and show you some improved Euler stuff right here. Notice that in improved Eulers, we said x equals x. So this is like our b plus m x is what that is like for our y equals mx plus b right here. We get a little bit of variable confusion because x is actually both our output and our initial position instead of actually that's really like our x value and y equals mx plus b. Here's the difference that I want to show you though. In improved Eulers, we computed m as strictly a slope from our f function because f is the differential equation. And when we updated x down here, this is when we multiplied by dt, delta t. We're going to change that for Runge-Kutta. For Runge-Kutta, we need to do a slope times dt so that this is representative of the adjustment to x, right? This isn't the direction that we're moving in. The direction that we'd move in is just f of tx. By multiplying by dt, it gives us the length of time at which we should be doing it. So this is like the direction of the vector right there. This gives us the magnitude of the vector. So this now is the entirety of the motion vector, the entirety of the update vector. So the important thing to notice is that when we do our x update down here, I do x plus our averaged slope, but notice there isn't dt on the end because the dt's were included in each of the terms along the way. And we have to do it that way because of the fact that our K2 value is dependent on knowing what K1's update instruction is. So this says do half of the update that K1 told us to do to x, use that as the x value to get our update that we're going to call K2. Then we're going to also go a half a time step in the future, and we're going to use half of K2's update to get us the full update that we call K3. Then for K4, we're going to go a full time step in the future. We're going to use the full K3 update to our position to get to our full K4 update for position. Then we're going to say, okay, now let's let our new x value be the old x value plus our weighted average of our 4 different updates that we came up with, where we take 1/6 of one copy of the K1 update, 2 copies of the K2, 2 copies of the K3, 1 copy of the K4. So since we added up 6 total parts, we divided by 1/6. I guess I could have just done that divided by 6 instead of 1/6 times, whatever. But again, notice this really important distinction here. This is a little bit procedurally different than improved Eulers in that we have to do the DTs incorporated to our components that we're averaging first. And since we've used those DTs, we don't need a DT sitting right here on the end. The DTs have already been incorporated in. Notice that what you can't do is just delete these DTs here and put them in out here because K1 has to have the DT in it to be used in K2 right there, right? So there is like a DT piece in K1. So it has to be on the inside right there as well. So we structure this a tiny smidge different than we did for that improved Eulers method where our DTs are going in a little bit different places here. But other than that, I hope that you can just kind of like don't get too bothered by the sort of fact that this is a pretty complicated diagram. This is just a diagram with 4 vectors in it, and we're taking a weighted average of those 4 vectors. I think that's a reasonable thing for you to say. Okay, we're taking a weighted average of four vectors, but it's a weighted average, so there's sort of six parts with the weights being involved. And again, all we're doing now is just saying we've updated x once, we've updated t once, throw the updated t and x into their corresponding lists, and then repeat that whole dang process right there 20 times. We compute a new k1 through k4 all 20 of the times, update x and t 20 times, put a new x and t in the list 20 times right there. So there's our Runge-Kutta method right there. It involves four update vectors. Each one is used to help find the next update vector out of the four. Only one of the update vectors depends only on our current time and position. The other three update vectors all depend on the previously found update vector. Notice K2 has K1, K3 has K2, K4 has K3. All four update vectors, we take a weighted average of them to get our new x position. And that all that action happens every single step, every single subdivision right here. Right. And a tiny note also, if you guys remember your technicalities from Calc 2 last semester, you should remember that Simpson's rule requires us to have an even number of subdivisions because it's grabbing points three at a time. We don't need that restriction right here because of the fact that here we use half time steps. So that is going to eliminate our need for that even number of subdivisions right here. So I'm going to go ahead and run this cell. And as we've been doing, let's just double check that like we didn't do anything crazy here. Our time list, again, is identical to our previous time list. We're counting by 0.2, getting out to 4. Our x list right here, let's see how our x values did. Where do we end with this one? I'm seeing here that we're ending at a little bit about around 49.5. Where did our improved Euler's end? About 48.5 right there. So we're pretty close to our improved Euler's method right there. They're off by about 1, in this case about 2% from one another. That's not too terrible right there. And again, remember our regular Euler's method, 33.3. That was not awesome right there. So we've got our estimates now from all three methods. So that's enough to make our three estimate graphs. We still want our one solution graph. So before we go to graph, let's grab our solution graph parts. I'll just call this 4 to continue with our naming trend to be the true solution. Here I am going, because I want to get a smooth curve and not one that only has 20 points on it. It's going to be all choppy. I'm going to use our NumPy library to make a linearly spaced t-list. It's going to start at 0, end at 4, and I want 200 points in the list just to get a really fine graph right here instead of the chunky ones that we know that we're going to get from our 20 subdivisions here. To get our x4 graph, all I want to do is get the x values that go with those time values. So I'm going to say, using the solution function that we wrote way up above, right? We wrote our solution function is the solution to the differential equation here, right? SOLN, solution at time t. Here we are. So I'm going to say evaluate the solution at time t for each of the t values that's in the t4 list. And that's in brackets, so that's going to produce its own list right there. So x, the final value of x, the x4 list would be our actual true solution to this, to what we're asking. What is x at time 4, right? But this will get all the time values and all the x values so that we can graph them all right here. So I'm going to run that guy right there. Oh well, okay. I don't think I need to show this one. Let's go ahead and look at our plot right here. For our plot, I'm not going to do anything you haven't seen before. We know that we're trying to graph 4 things on one graph, and so there's my 4 plot.plot commands. The first graph is going to be our first time list and our first x list. So this is going to be Euler's method. I'm going to make Euler's method a green dashed line, and I'm going to give it the label of Euler's so that when I call the legend call later, it knows what label to use. The T2 and X2, the 2's, were improved Euler's. I'm going to make that a red dashed line, and we've got our label for it right there. The 3's was Runge-Kutta, our big guy today. I'm going to make that a blue dashed line and give it the Runge-Kutta label. And finally, we called the true solution, the actual solution, T4 and X4, K with a single dash instead of a double dash. We'll just make that a regular line. And K is the one letter shorthand for the color black, typically because blue is used with B, and so K is used with black because BLUE, I don't know, you don't really want to reuse, I don't know. K is pretty unique to black, and so that's why K is our black letter right there. And actual solution is my label for that guy. I like to turn on my grid. I want to turn on the legend, which is going to read off all of the labels that we stuck onto each of those plot commands. And I'm going to want to adjust my axis just a smidge right there. Honestly, I think we could do without that line of code and it wouldn't be a big deal. I just don't like it when my graphs go literally corner to corner. I want like a little bit of breathing room, so that's why I sometimes adjust this. Remember that this is a function, so it's in parentheses. This function takes in one object, which is a list, so it's in brackets. The four things that need to be in that list are xmin, xmax, ymin, ymax, just like you're doing your TI calculator stuff. And we know that to see the graph, we need to ask Matplotlib to show it at the end. So let's go ahead and run this guy and see what we're going to see here. All right, so what is it that we're seeing right here? So as I said, I hate it when my graphs actually end up in the corner, which is why I extended this to 4.5 instead of just 4 so I could see it. What you guys should be able to pretty easily see here is that Euler's method fell off pretty hard right there. And we saw that. We knew that it was getting, gosh, I wish it would stop highlighting like this. We knew that 33 was about what we were getting for our final estimate right there for Euler's method. And I can see that height of 33 at time 4 here. We can see that the others look very, very similar to each other. So what I can see is my red dashed line for improved Eulers looks really close to the true solution, but definitely I know that you guys can see that it's technically under it a little bit. I can see the error. There's not a lot of error, especially compared to Euler's method, but like I can see it. You guys should notice that you cannot see the Runge-Kutta method on here at all. The blue dashed line does not appear to be showing up. But what I'm suspicious of is it's just killing it and that we're just laying on the actual solution. So here's my easy way to adjust my graph to check that. I'm going to go ahead up here. This line of code right here is my true solution. So I'm just going to make it a comment so that it doesn't actually get evaluated as code. So this should now just redo the graphing process, but only give me my 3 estimates right here. And yeah, now you guys can see that blue dashed line. The blue dashed line was literally just sitting underneath the estimate because it was so dang close to the right answer that those two graphs were right on top of each other right there. By the way, I want to point out to you guys that the order in which you plot things does affect like your layers on Matplotlib. So if I were to plot this thing first, it would be underneath because that's literally like you saying draw with a pencil this curve first. Then later draw with a pencil this curve, which we know is going to lay over the top of it. So I think if I do it in this order, we'll be able to see. In this order, I doubt you guys can see it on your screen, but for me, I can clearly, this line looks like it's blue instead of black right now because the blue dashed line got drawn on top of the black instead of the black solid line being drawn on top of the blue dashed line. And that actually is kind of helpful. I find that occasionally just reordering the ordering of my plots helps me see things better because it does have layers as if you're drawing with a pencil over top of other graphs out there. So this is good. What this is showing me is that Euler's method sucks just like we thought. Improved Euler's is very obviously better than Euler's, but still isn't quite there. Runge-Kutta is literally like nailing our solution with only 20 subdivisions. It's doing an excellent job with only 20 subdivisions right there. It's doing even better than improved Euler's, quite visibly, in fact. So that's pretty good. So I hope that what you're taking away from this is Runge-Kutta is obviously better than improved Euler's with the same number of steps, right? If we're using 20 steps for all 3 of them, Runge-Kutta is going to be way better, and Euler's method just sucks unless you're doing like a huge number of subdivisions. There's nothing that's going to be good to do Euler's method with 20 steps. That's basically always going to be kind of bad for you right there, like this one was. So what I'm really more interested in, though, is looking at errors today, right? So what I want to know, again, is this. What I'm not so interested in is what percent better did improved Euler's do than Euler's? What percent better did Runge-Kutta do than either of the other two? Stuff like that. The reason why I'm less interested in that is because that's dependent on our number of subdivisions as well as the function that we're looking at. If we're going to look at functions that have bigger and smaller steepnesses, that's going to affect the amount of error that we end up seeing because having more steep functions with a large number of subdivisions with a large dt means you're going to fall off earlier because if the function gets steep, has a high like second derivative, then we're going to see an Euler's method, a vector that just points out here when it should have gone up. Because improved Eulers and Runge-Kutta look ahead, they're going to see that change coming and they're going to tend towards it more quickly. So just getting functions that have steeper solutions makes Euler's be even worse. or less steep solutions makes Euler's method not be so bad. So that's why I'm not super interested in comparing across techniques, because it sort of depends on even just the individual function we're looking at, not just the number of subdivisions. However, if we're comparing within one technique between number of subdivisions, we can get an idea for how these techniques improve as we increase our number of subdivisions. And that's the thing that's really valuable to us, to know which of these are excellent, all right? So to look at the errors, here's what I want to do. What we want to do is let's save the final estimates that we got above. So we made x1, x2, and x3 as lists. The last object in each of those three lists is our final estimate for Euler's, improved Euler's, and Runge-Kutta. I want to save those so that I can overwrite those lists here in a minute. Then I want to repeat this whole entire process. All the code from up above, I'm going to copy and paste my life away. And the only thing I want to change is I want to update to having 20 subdivisions, or sorry, up to 40 subdivisions instead of only 20. So we're doubling our number of subdivisions. Then I want to use the final 3 estimates from the 20 subdivision scheme and the final 3 estimates from the 40 subdivision scheme. We're going to get the 6 errors relative to the true answer for all 6 of those estimates. And then we're going to do the division. We're going to say, what happened to my error for the Runge-Kutta method for the 20 versus the 40 subdivisions? How many times better did we do when we doubled our estimate? All right, that's the question we want to ask. So the first thing we want to do is I'm going to save my final estimates from the 3 methods as their own variables. So what I'm doing here is x1 is our Euler's method estimate list for 20 subdivisions. The last thing in the list, the thing located at -1 index, that's going to count backwards by 1, so it's going to start at the end. This is going to grab the last object in the x1 list, and I'm going to save it as, notice it's a lowercase x right here because it's only one value instead of a list. It's the x value from Euler's method associated with 20 subdivisions. That's my naming idea right here. It's final x1 with 20 subdivisions, final x2 at 20, final x3 at 20. And just to kind of verify that I did the right thing, I'm going to display all 3 of them at the end with that last line right here. So let's go ahead and run this, and we can see we are getting the 3 numbers we've seen. That 33.33, that was our Euler's method estimate with 20 subdivisions. The 48.35, and then the 49.59, those were our final estimates from the improved Euler's and Runge-Kutta up above. So this is just me. These 3 variables now are holding our final estimates from the 20 subdivision scheme. Now we're going to repeat 100% of the above code just by copying and pasting it all into one giant cell. The only number I'm going to change is the number of steps is going to go from 20 to 40. We're going to recapture the 3 final estimates with the 40 subdivision scheme, just like we did right here. We'll use all 6 final estimates to get our 6 errors. We'll compare some errors. All right, so we've done this code right here. So now, this is just a mountain of copying and pasting. 100% of this code up here was just copied and pasted, and the literal only thing I changed was steps is now 40. All the rest of this is the same. So our initializations, going from 0 to 4 with 40 steps, getting our dt. We're going to do Euler's method, literally copied and pasted that block. The only thing I added was just a label right there. I made no changes from what you saw up above. Improved Euler's, copied and pasted this block exactly. Made no changes, just gave it a comment label right there. Runge-Kutta, absolutely no changes from up above right there. Just copied and pasted the whole beast in there. Put Runge-Kutta as my label right there. And notice that what we did, though, the important thing here is I'm doing maybe like a slightly bad programmer thing, and that I am overwriting all of our old x1, x2, x3 lists, time 1, time 2, time 3. Well, but I'm sort of like losing our old stuff, but I kept the thing I needed. The thing I needed was I wanted to compare final estimates right here, and I'm keeping this information intact by saving it as another variable. So a real programmer would probably yell at me for throwing away my old results and overwriting them by reusing these same variable names. Like, this is my bad line right there where I don't know, whatever. The point, it doesn't matter to me because I've saved the information that I needed, but recognize that by running this one giant cell, I'm kind of wiping away all the stuff that we collected up above. But again, we salvage the parts we want right there. So I've got the stuff I need to keep. So I'm going to go ahead and run this. So I put all this into one cell because I'm not thinking anymore. I'm just redoing a process that I already know works. I know that the only thing to change was just the one parameter, went from 20 to 40. So let's go ahead and run this guy. Now I'm going to save the final estimates for each method with 40 subdivisions. You should notice that this is just more copying and pasting right here. And you can tell it's copying and pasting because I even forgot to update my labels down here. These should each be 40, right? So I'm grabbing the final thing in the x1 list, final thing in the x2 list, final thing in the x3 list, and I'm saving them as x140, x240, x340, right? And let's take a look at each of them right here. Now, what you can see is we're doing better. No, remember that this one was like the 33.33. It's now up to 40 for Euler's method for our final estimate right there. Euler's method's doing a lot better. Notice both of these are very close to one another, about 49 and a half. And in fact, remember that Arunga Kutta with 20 subdivisions? Look at that. 49.5946 with 20 subdivisions. Remember that number. 49.5956. 49.5979. It even matched for going from 20 subdivisions to 40 subdivisions. Doing only 20 subdivisions already got it good to go. I'm even out to 2 decimal places. We only even changed at the 3rd decimal place, going from 20 to 40 subdivisions on Runga Kutta, because it nailed it with only 20 subdivisions pretty much already. That's pretty sweet. Like these other ones, like kind of changed meaningfully. This Runga Kutta was like already there. So we've got our 6 final estimates for 20 our 3 final estimates for 20 subdivisions, our 3 final estimates for 40 subdivisions. Now let's find the errors corresponding to these 6 final estimates of x4 that we've made. So our actual solution is just using the solution function that we wrote and evaluating it at time 4. That's the true solution that we're comparing against. I'm going to get my error using Euler's method with 20 subdivisions to be my estimate with Euler's method at 20 subdivisions minus the actual answer, and just taking the absolute value in case there's any plus or minus. This means I don't have to think about positives or negatives. That's not what I care about right here. I want to know distance from correct. And so I'm just following the same scheme right here, right? E123, 20, 20, 20. X123, 20, 20, 20. E123, 40, 40, 40. X123, 40, 40, 40, right? So that's going to get me my 6 errors from my final estimates to their actual true solution, right? So let's go ahead. Wait, did I run that one? Yes, I ran the last one. Let's go ahead and run this guy. And again, nothing quite to see here, but what I want to do is now ask the most important questions. This is the stuff that I care that you remember to take away from in this class right here is how do these get better as our number of subdivisions increases? So first want to check Euler's method. What happens to our error when the number of subdivisions is doubled? So I'm taking my error from Euler's method with 40 subdivisions, which I expect to be smaller than my error from Euler's method with 20 subdivisions, and doing the division. And what do we see? 0.574. Now, if you remember my claim from last video, the claim was that double the subdivisions results in half the error with Euler's method. 0.57 isn't quite half, but I hope you can believe that this isn't going to be exact all the time. That half rule isn't exact. It's an estimate. I'm going to make that get better, and I'm going to make you feel better about it in a minute right here. But I am going to write what we should be concluding here, which is I'm going to say Euler's method, order 1 numerical method. That is how am I going to write this? Do n times as many subdivisions, get, well, I don't think, get 1 over n times as much error. Right? So since we did 2 times as many subdivisions, we got 1 over 2, or 1/2 as much error, about right there, right? 0.57. Right? And I'm going to want to copy this because we're going to make very similar statements here in a second. All right. Now improved Euler. So same thing. Using method 2, our final error with 40 subdivisions, using method 2's final error with 20 subdivisions right here. And we do the division. And what you should remember from our previous video was that we said that improved Euler's method actually had like an n² relationship. You should notice this being really close to 1/4. 1 over 4 is 1 over 2 squared right there. In the last video, we even did it where we did 3 times as many and we got 1/9. Right? So in this one, I think I can say here, improved Euler's method. It's an order 2 numerical method. And that's because if you do n times as many subdivisions, you're going to get 1 over n² times as much error. So 1/4 as much error in this case right here, because we did double. So if we did triple the number of steps, we get 1/9 the error right there, right? Finally here for the Runge-Kutta method, what happens to error when the number of subdivisions is doubled with Runge-Kutta? So once again, E340 divided by E320, and here we're getting 0.0679. Now I don't expect that you recognize this as a fraction right here, but I'm going to suggest to you, what do we think RK4 stands for? Well, it stands for the fact that this is a fourth order numerical method. This is an order 4 numerical method. We're going to get 1 over n to the 4th times as much error. That's awesome. Our error is getting better by a factor, or by a power of 4 instead of just linear growth or quadratic growth, or decay, I guess, in our error size right here. This is excellent. This means that our error is getting tiny real quick right here. And so one thing you guys should see is, since we doubled, you guys know that 2 to the 4th is 16. So we're expecting to get 1/16 the error by doubling our number of subintervals. And here's that decimal for 1/16, 0.0625, 0.0679 right there. So this is pretty close to 1/16 right there, justifying that this is an order 4 numerical method, which is why we call this RK4. It's not because it used 4 points to make our estimate. It's because it's a fourth order numerical method right here. Now, these decimals I don't think should be very convincing to you, that decimal is representative of a half and that decimal is representative of a quarter. So all I want to do for the last part of my little piece of this video right here is I'm going to go up and change our numbers so that we get numbers that are really close to 0.5, 0.25, and 0.0625 right here. So let me just rerun some code right here and we'll be like, oh yeah, we nailed it, and we'll feel really good about our wrap up right here. So going all the way back up to the top, all the way back up to the top, all the way back up to the top. We're good here, we're good here. I'm going to change this to 2,000, and then we'll do 4,000 for the other one down there. So rerun, 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 rerun. Notice when I plot it all, they're all just sitting on there because 2,000 subintervals. I mean, of course, they're all going to do a pretty good job right there. Even Euler's method's going to be doing a great job with 2,000 subintervals, so that's not terribly surprising for the graph. So now we're going to rerun all this stuff, and notice, like, look at their final solutions. Man, look at regular Euler's is still kind of far off from like the other two right here. The 598, 598 is still sitting at 38. Now this is the only other thing to change. Changing our number of steps to 4,000 for our second run through right here. It still ran like pretty much automatically right there. No time to run that. Getting our final estimates. And notice again, 5981, 5981 for improved Euler's and Runge-Kutta, still 4891, still kind of off by a whole 0.1 and then some with Euler's method, even with 4,000 subdivisions. So now let's look at those errors, and now we're going to see some real nice values come out right here. Oh yeah, that's 50% of the error right there. I hope you're much, much more convinced about that. Oh yeah, that's 25% of the error right there. I think that you're more convinced there as well. And wait a minute, what just happened to our Euler's stuff right here? Why did that not? What happened right there? Did I not run one of my lines of code or something like that? What happened to my Runge-Kutta stuff here? Did I use that number 20 in here? That's weird. Oh man, I hate it when things fall apart in my literal last 1 second of the video right here. What is up with that? It should just be our final thing in each of the cases right here, right? I didn't change anything else. I did just grab the last object in each of those lists. We're doing the number of steps for each of the thing, and I did appropriately set steps equal to 4,000. Let's see, I don't feel like I saw this when I did this earlier. Let me do this with 200 and 400 and see if I see. I thought I got exactly what I was expecting to get right here. I mean, so one of the things that I'm thinking is possible here is that Runge-Kutta is so honed in that the number of decimals that Python is by default holding, it can't even measure the difference between the solutions at that number of decimal places. So maybe this is saying we got so accurate that the numerical estimate... No, now something else weird is happening here. I must have hard-coded in some value without realizing it because I just saw another bad value in there. Ah, how did I get this wrong at the last second? You got to be kidding me here. Steps is the only thing I changed. I didn't do anything different here. There's all of our new values. Dang it. There's all of our new values, dang it. Steps never shows up anywhere else. Even 200, Euler's method is still off by a little bit right there. It's grabbing the last thing in the list. So notice here, it's not like I ever said like at index 200 or index 199. I'm grabbing the last thing in the list. These are our close to final estimates right there. Now with 400, right? I am at 200, right? Man, it's a bummer when I end up with smidgens of errors in my code here. 400 steps, TF, TI divided by steps. Ryan range steps, Ryan range steps. It didn't change anything. I straight up copied and pasted this from above. There's no way it's anything different. I literally ran all this code right before I did all this and got all this stuff exactly like I expected it to be. And now I'm not seeing that. I'm wondering if I ran that too fast and it wasn't done running this one before I ran my later ones to get these values right here. And it used the old values. What in the world happened right there? So now we're getting things that are closer to those values. I'm annoyed by this. I want to run this all one more time. I think that what happened there is maybe I ran this too fast, so it was still running a previous cell when I ran a next cell, and it used some incorrect values maybe. But this one shouldn't depend on anything. That one shouldn't depend on anything. Done running. That's good. That's all good. I'm going to save them because we're done with all that stuff. That's all good right there. And now I'm going to update this to 4,000, but I'm going to watch that thing at the top right there and see, oh, it is like done. Being nice and patient and slow. 50%, 25%. All right, there might be something a little bit funkier going on right there again. I could potentially see that, and maybe here's my thing to look at right here, which is what is my E340 right now? So E340 right now is really holding what I would call E3 4000. I think this is going to be our issue right here is that we've actually reduced ourselves to so little error by now. This is 3.666 times 10 to the negative 12th right there. That's how much error there is. I think that because Python is only holding like something like 15 decimal places and we have error that goes out to like the 13th decimal place before it even starts, I'm thinking that the reason that we're not seeing our trend be appropriate right here is only because of numerical cutoff error because of how good Runga Kutta is doing right there. So this is our correct thing that can be proven. Once you guys go to grad school, you're going to prove that the limit as our number of subdivisions goes off to infinity. If you take n subdivisions versus n divided by 2 subdivisions, that the limit of the errors of the two's ratios will tend towards 1 over n to the fourth for any smooth function that's out there. We're just not seeing that here because it's literally so close to the correct value that it's got cutoff errors introducing us just an incorrect answer right there, basically, I think is all that's happening right there. So this is basically our big deal here, though. Linear change, quadratic change, fourth order change, right? So Runga Kutta method, way more powerful than our other methods right there. Doubling the number of subdivisions gets you only 1/16 the error that you previously had versus a quarter the error or a half the error that you previously had. So this is why Runge-Kutta method is heavily preferred. It requires this extra bit of bookkeeping of K1, K2, K3, K4 each step of the way, but you can get away with doing a tiny fraction of the number of subintervals you used to have to do and still end up with negligible error. I mean, so little error that it's hard to analyze the error using Python because it's such a small number that Python's not holding it. There are ways that we can get Python to hold longer, more accurate decimals here. I don't think that's worth our time to go into right now. So I'm going to wrap it up here, but these are our big conclusions to be taking away here. Euler's method is an order 1 numerical method. Improved Euler's is an order 2 numerical method. Runge-Kutta, RK4, fourth order numerical method. Vastly better than the other two methods right here. That's why this is the standard that is used for any general numerical methods for differential equations. The only other thing I'll say here is that the default is to use RK4 in any given setting. There are plenty of different types of differential equations, systems in particular, that come up that actually have sort of like custom numerical techniques that work particularly well for them. For example, if you know you're going to have trig parts in there, or if you know that you're going to expect to see incredibly steep slopes, stuff like that, then maybe you want to look further out into the future, or I don't know, different things like that. So certain types of families of differential equations have sort of like custom numerical methods that go along with them. But for the most part, if you're just doing something generic for an early analysis, RK4 is the standard for a generic numerical method to estimate these things here. So in the homework, one of the things I'm hoping to ask you guys to do is to look at a system of differential equations, to apply each of the three techniques, produce three graphs, see that one of your graphs sucks, one of your graphs is mediocre, and one of your graphs looks perfect. That's the thing that I'm hoping that we'll be able to demonstrate with a thing in the homework here. So I am interested in you guys being able to reproduce these things here. And maybe I'll leave my screen on the Runge-Kutta method as our last one right here, since this is the one that you guys are going to need to probably reference here the most for your upcoming assignment. But this is sort of our wrap up here for all of our techniques. You guys can see above me, I think I talked through this in the last video, but I'm not sure, so I'll say it right now. Week 8, this week is our last week before spring break. Much to my wife's dismay, there's still a baby inside of her, which means that we're still doing this week. We've got spring break the week after that, so you guys can do your catch up. I'm going to make sure that this homework assignment doesn't do until after spring break instead of before, so that if you guys want to spend spring break, I know that this coding stuff is probably taking some of you guys some time out there. The week after spring break is going to be baby week, meaning no new content, but you guys will have a midterm test that week. That'll be the only thing. My plan is either Sunday or at the end of spring break, Sunday after spring break, or even maybe the Monday, the week after spring break, I will send you guys a Canvas announcement. And in that Canvas announcement, I'll say something like, your tests will be posted in Canvas on Tuesday or on Wednesday at this time, and you will have until this time to submit it back in Canvas. So I'm thinking you guys will get like Tuesday to Friday or Wednesday to Friday or something like that to take the midterm. And I'll tell you guys about it on Sunday or Monday beforehand so that you know when you need to be in Canvas taking the midterm. The week after spring break is when we will return to our regular content. And since we are wrapping up our numerical content right now, that's going to put us into back to section 3.1, since we sort of left off with chapter 2. So we're going to be starting chapter 3. Section 3.1 is the same across both editions of the textbook right there. Introduction to linear systems. So chapter 3 is a heavy focus on systems, but very specifically only on linear systems. So ax plus by, cx plus dy are going to be our two equations for the whole chapter, and we're going to look at all the magic that happens with those guys there. So this is my last video here for about 2.5 weeks, because I'm not making any this coming Thursday, Friday, because it's spring break after. Not making any that Thursday, Friday, because that's spring break week. I will make them on Thursday, Friday after that, because that'll be baby week that I'm making them to go into the next week, the chapter 3 week out there. So hit me up with your programming questions. I'll be hitting you up about the midterm that you are taking the week after spring break, and that is the only thing that you have to do the week after spring break. I will see you in the next video, which will be section 3.1, 2 weeks after spring break. Have a good one, everybody.